Hi everyone! This video is dedicated to some preliminary theory for solving first-order differential equations. We're going to look at the general form of a first-order differential equation, and I'll tell you what an initial value problem is. Let's begin by looking at these four equations and determining which ones are the first-order differential equations. And you may want to pause this video and try to answer this question yourself. But I'm going to continue. Well, all of these equations are the first-order differential equations. Let's verify these equations one by one. In equation A, I can see the derivative dy dx. It's the first-order derivative, and this is the only derivative present in this equation. So yeah, that's the first-order differential equation. In the second equation, I can see y prime. It's another notation for the first-order derivative. And since it's the highest order of the derivatives present in this equation is first-order differential equation. Equation C, again, I can see dy dx, first-order derivative. Overall, that's the first-order differential equation. And equation D, now I don't see the derivative itself. I can see differentials, dy and dx, but I can rewrite this equation so that I obtain the derivative notation dy dx. For that, I simply have to divide by dx all terms of this equation. In this matter. So I'm going to get x squared dy dx plus 2xy equals 0. So we just confirmed that these are all first-order differential equations, and this is what we're going to do next. We're going to rewrite each of these four equations such that the derivative is by itself on one side, on the left-hand side. So let's isolate the first derivative for each equation. To do that, for the first equation, I just simply have to add 2y to each side. So I'll say rewrite dy dx equals 2y plus e to the power 3x. Okay. Now for the next one, to isolate y prime, I have to subtract 2y first. So I get y prime equals 1 plus x squared minus 2y. I don't have any like terms to combine. And then finally, I'll need to divide by y, right? To get y prime by itself, I'll divide the left-hand side and the entire right-hand side by y. So this way I get y prime equals 1 plus x squared minus 2y over y. Okay, now next one. I'll simply have to divide by e to the power x on each side, so dy dx is 2x over e to the power x. And the last one. First, we're going to subtract 2xy from each side. I get x squared dy dx equals negative 2xy. And finally, I need to divide by x squared on each side. So I get, I'll write it here. So next I will get dy dx equals negative 2xy over x squared. So the first derivative is by itself on the left, but I can see that I can still simplify the right-hand side, right? I can divide out x. This way I get dy dx equals negative 2y over x, like that. Now, why did we have to do this kind of manipulation with each equation? Well, the only purpose as of right now was to show you that while these first-order differential equations look different, they have one form. And that form is the following. The left-hand side, and that was something that we did ourselves, the left-hand side is the first derivative, right? For all of those, where's my fourth one? Right here. The left-hand side, the first derivative. And what is the right-hand side? Well, the right-hand side, I would say some kind of expression involving y, x, those two variables, and some numbers, some constants, some operations, right? So for all of those, now here it's only variable x. For the third one, here it's again x and y. So my hope is that you observe all those four equations written this way. When I write the first order differential equation in general form, it will make sense to you. So I'm going to put it here. So this is how the general form looks like. It's dy dx on the left hand side. Well, it's a first order differential equation, so that's the first derivative. And the right hand side is the function of x and y. Now we said, well, we have expression in terms of x and y, but we treat that expression as a function in terms of those two variables, x and y. In the differential equation where the right hand side was only in terms of x, we can just simply call a special case of this general form. To connect us with the next portion of this video, let's do the following example. Here we need to verify that all members of the family of y equals 1 over x plus c, remember it's the family of functions, are solutions of the differential equation y prime equals negative y squared. And I want to go back to this family of potential solutions. When we replace this arbitrary parameter with specific numbers, well, we're able to see different members of this family. And by the way, some of them are shown here. The graph of this function always comes in the form of two symmetric branches, and what that arbitrary parameter does is just shifts that graph right-left. That's why, you can see how they're kind of parallel to each other. And we can easily imagine that c can take upon infinitely many values, so there are infinitely many members in this family of functions, and there are just a few of them here shown on this graph. Okay, let's move on. Let's verify that this family of functions represents solution to this differential equation. Remember, for that we have to plug in this function and its derivative into the equation. So first I will obtain the derivative. So I will rewrite the function again, or the family of functions, I should say, 1 over x plus c. We'll write it in this form. And now I have to find y prime. So to obtain the first derivative, we have options. We can either use the quotient rule, or we can rewrite this function as x plus c to the power negative 1. Either way, we're going to get the same answer. I think I'll go with the quotient rule. So here's the quotient rule itself, just in case if you need a reminder, and then that's how I'm going to label numerator and denominator. So f is the numerator, and then of course g is the denominator. Okay, let's follow the rule. In the numerator, I have to take g and multiply by f prime. So derivative of constant 1 is 0, so times 0, minus f, that's the numerator, times derivative of g, which is the denominator. So derivative of x is 1, plus c is the constant, right? So it means that derivative of that will be 0, like that. And in the denominator we have x plus c squared. So that is in the numerator. Okay, first of all, that just 0, so it disappears, and here I have negative 1 times 1, so negative 1 in the numerator, and then x plus c squared in the denominator. Okay, so that is y prime, and now I'm ready to plug that into the equation. Y prime I'm replacing with what I just obtained on the left hand side, and on the right hand side we have to plug in what y equals to right here. Okay, so the left hand side is the first derivative, negative 1 over x plus c squared equals, and the right hand side, just be careful here, since I don't have any parentheses shown, it means that that second power only applies to y itself, not that minus sign. So I will put minus sign, and then I will place what y equals to, which is 1 over x plus c. inside the parentheses, and then I square that. So only that is being squared, not the minus sign. And let's simplify that. So from here, I'll get the left-hand side is negative 1 over x plus c squared. And as you can see, the right-hand side, yeah, it turns out to be the same. 1 squared is 1, and I will place that negative sign right next to it so that it matches my left-hand side a little bit better. And then the denominator squared is x plus c squared, like that. So as you can see, the left-hand side equals the right-hand side, so that confirms that the given family of functions represents solutions of the differential equation y prime equals negative y squared. But we have more to this example. So we also have part B, and this is what it says. It says, determine solution that is subject to the condition y of 1 over 2 equals 2. What does this mean? Okay, so first of all, we confirmed that the following family of functions represents solutions to that equation, right? But we're being asked to determine solution that's specifically subject to this condition. Now, what is this condition? Let's try to understand it. Well, this is function notation. And remember, for the function notation, the only thing that we don't say f of 1/2, we say y of 1/2, which is same thing. What we have inside the parentheses, it always represents x value, and what function notation equals to or represents, that is y value. So basically, it says the following. Yes, we know that this is the family of solutions to the given differential equation, but this family has infinitely many members, infinitely many functions, right? And we're asked to find one that will contain this point. So we need to find such function that when x is 1/2, y equals 2. How do we find it? Well, it's actually very simple, because what we need to do, we need to plug in point, plug 1/2 to this point. Well, again, that's x and y, the given x and y values from here, into, well, this family of functions. And once we do that, we're going to identify what value of c satisfies this condition. Because when we have c in our answer, it represents family of functions. When c is a specific number, well, we're looking at the particular solution. Let's try it. So we're going to take 2, and we're going to plug that in for y. And we're going to take 1/2, and we're going to plug that in for x. So that way, we'll get the following equation. 2 equals 1 over 1/2 plus c. And now we just have to solve this equation. Let's simplify the denominator by adding 1/2 and c. How do we do that? Well, we simply have to rewrite c as a fraction, so I'll put c over 1. We know that to add two fractions, they both have to have same denominator. Well, the LCD will be 2. So we'll adjust the second fraction. That means that I'm basically adding 1/2 plus 2c over 2. And when denominators are the same, I'm ready to add two fractions. So it's 1 plus 2c over 2. That's how the denominator will be simplified. So from here, I get the following equation. 2 equals 1 over, and now in the denominator we have 1 plus 2c over 2. Now, once we simplify the denominator, we're ready to simplify this complex fraction. And when I'm dividing 1 by a fraction, it's the same as taking 1 and multiplying it by its reciprocal, right? So that means that from here we're going to get 2 equals 1 times, I'm not going to write it because 1 times anything will not change that, but it's going to be 1 times, and then I'll flip the denominator, so it's 2 over 1 plus 2c, like that. So I multiplied 1 by the reciprocal of the denominator, and that's what I got on the right hand side. Next, I would want to get rid of this denominator on the right hand side, and I can do that by multiplying by that denominator on the right and on the left. So plus 1 plus 2c on the right hand side, and then times 1 plus 2c on the left hand side. So that cancels the denominator on the right, and we get 2 times 1 plus 2c on the left and just 2 on the right. Okay, we're almost there. A few options here. I think I'll just distribute 2. So that's going to be 2 plus 4c equals 2. Now, from here on, it's pretty simple, right? Because I need to subtract 2. I'm trying to get c by itself. I'll subtract 2 from each side. Oh, I noticed that it's actually cancels the right hand side as well. So 2 minus 2 is 0. So it's 0. 4c equals 0. Okay. And then once I divide by 4, I see that the arbitrary constant or arbitrary parameter has to be equal to 0. Okay, what does this mean? I'm going to box this. Hopefully, you remember what we started with and why we're doing all that. Remember, we're trying to find the value of this arbitrary parameter such that a function satisfies the given condition or contains this point, in other words. And we found that c has to be equal to 0. So that means the function itself, I'll put it as an answer. And then, we'll talk a little bit more about it, but I'll just say, well, that's technically an answer. A function has to look like this. Y equals 1 over x, and then plus 0. What I did, I just literally replaced the value of c that we found in the function, right? X plus 0. And of course, I don't really need to write plus 0. So it's y equals 1 over x. So that is our answer. So that is the function. So what's the meaning of that answer? That's the function from this family of functions. That particular function also one of the solutions to the differential equation. But besides that, it satisfies this condition. Y of 1/2 equals 2. In other words, in this function, when x is 1/2, and think this way, when x is 1/2, so if I put in the denominator here 1/2, I'll have to take reciprocal, and I will get y equals 2, right? See how it satisfies this condition? So that's why it's the answer to the question for part B. I also want to show you, actually we can see this function or see that particular solution on this picture. So y equals 1 over x, that basic reciprocal function. Let's see, it's the one that's over here. That's one branch. And let's see, let me find the other branch. It's this one. So these are the branches that don't cross either x or y axis. So y equals 1 over x. So it presents on the picture. And not just that, but on this picture, and it's a really tiny picture, but still I can see, or at least I can see that the given condition, x equals 1/2, y equals 2, that's that condition, or in other words, that point is on that graph. So 1/2, 2. 1/2, 2, I don't know if you're going to see that or not, but 1/2, 2 is this point here. And it's right on that graph. So it's point 1/2, 2. So basically we can confer it geometrically, like visualize that. But the point of that example was to illustrate what's called the initial value problem. The initial value problem will ask you to find a particular solution to the differential equation that satisfies certain condition. And the condition will be given in this form. So find particular solution to the given differential equation such that that solution contains certain point. This is a very common type of problem that we solve in the differential equation course because it has a lot of applications. So we'll see a lot of problems like that throughout the course. But here's its official definition. I would like to point out that this definition is given to us in terms of the first order differential equation However, the initial value problem exists for higher order differential equations as well. But yeah, going back to this definition. So basically, this is what it says. It says solve the given differential equation that's subject to the following condition. So in this condition, of course, it's all written in general here, but basically x sub 0, y sub 0, those two represent certain values or certain numbers. So hopefully you can recognize that and connect that to the example that we just did, where x sub 0 is a number in an interval I, and y sub 0 is an arbitrary real number. And it also says here that in geometric terms, we're seeking at least one solution of the differential equation defined on some interval I, such that the graph of the solution passes through a prescribed point x sub 0, y sub 0. And again, hopefully, while this is all given in general, hopefully you can see connection with the example that we just did. So all those lines represent solutions to the differential equation. So let's say family of solutions. But then we're looking for one particular solution that specifically contains that given point. And I also would like to point out the name of that problem, initial value problem. Well, it's called this way because this condition, it's called initial condition. So you're starting to solve the problem already knowing something about solution that you're trying to obtain. Okay, so now you know how the general form of a first order differential equation looks like, and you know what the initial value problem is.